Okay, we'll pick up where we left off at section 2.4 in the textbook. Discussion of matrices, arrays, and working our way through, I believe, ODEs and some final math review topics before we get into more discussion of MATLAB and new numeric topics. So a matrix, obviously, if I can go over here to the document cam, a matrix is really just a two-dimensional array. It stays in two dimensions, so you can have a 3, 4, 6, 12, however many dimensions of data you want to have. A matrix mathematically is really specifically talking about just two of these dimensions as far as linear algebra is concerned. We'll go over some of the basic operations, but know that the notation follows the standard. Whenever you see like each subscript, this is, for example, top left corner is A11, that means first row, first column. A12 means first row, second column, so on and so forth. So you see A1N, that represents, it can be any size. So first number is row, second number is the column, and that's how they reference the locations in each individual matrix. Very standard notation. You'll see that all over every mathematical textbook. Matrices do have some differences from normal mathematical multiplication and operations. For one, you can't just switch the order of multiplication haphazardly. You can, however, multiply them by a scalar without any issue. If you want to take any given matrix and just multiply each one of its numbers by a constant, that is the same thing as multiplying the entire matrix itself by a scalar. What I mean by that, if we can go over to the surface real quick, is that if you want to say 5 times a 2 by 2 matrix, so just make one up, this equals 5, 10, 15, 20. Pretty easy. You just take 5 times each internal element, and that's a scalar multiplied by a matrix. Not a big deal. If you want to add matrices together, as given in the example right above figure 211, you add each individual element of one matrix and another. They have to be the same size for this to work. So if it's 3 rows, 2 columns, the other one you're adding with it has to be 3 rows and 2 columns as well. You can't have a size mismatch for matrix addition. So you can see in each one of those elements they just added the top left component, the 1, 1 component, the 1, 2 component, 2, 1, 2, 2, etc. For whatever size of matrix you're doing, whether it's in MATLAB or by hand or whatever piece of software you're working in, that is how you have to perform matrix addition. I'm going to go through some of these concepts pretty quick because they're simple and it doesn't take a lot to pick them up. You can sit there and read about matrices for a long time and it can be confusing, but if you really just have someone explain the basics to you, you can pick up pretty quick. I hope that's the benefit you're getting out of these videos. Transpose. This is a very graphical type operation where you take the diagonal. So in this case, right above figure 212, the diagonal would be straight through the numbers 2, 3, and -4, starting at the 1, 1, 2, 2, 3, 3 locations. This is a nice example for transpose because it actually changes the row and column count of that matrix. So you flip the entire matrix along that diagonal, if you think geometrically, with a geometric mind, I guess is the way to say it, and that's it. Not really a high-tech mathematical concept. You notice that the -1 and 5 have switched locations, 6 and 0 have switched locations, and you just flip everything about that diagonal location, including the aspect ratio of the matrix itself. That's really all there is to a transpose. Obviously, if you take the transpose of a transposed matrix, you end up right back where you started from. Nothing happened. Okay. Multiplication. This is the first place that we really need to slow down a little bit to teach you perhaps a new process for those of you who haven't had a linear algebra class or much exposure to this before. So if you are going to multiply a matrix, you can perhaps enjoy the written description of multiplying m by n and what dimensions can match with others, but really what it comes down to is that the number of columns in the left matrix, in this case it'd be A, has to match the number of rows in B. If it doesn't, you can't do it. Like if you switch the order of A and B here to multiply one by the other, it's not going to work. So let's go through and do this. Probably they have a small example. Yeah, over here on the right. This shows very specifically how you go about doing matrix multiplication. You take an element one at a time. So you go through the first row initially. So 2 is the 1, 1 element of this matrix times 1, 1 of the second. 2 times 4 Notice that's the first element we've listed over here. And then you add on -1 times -5. And those two components added together make up the solution set for the output matrix. So really, if I can lean over, you're going across the top of one matrix as you go down the other. So the A matrix, the leftmost matrix, you'll be just reading right across the top row, and then the middle row, and then the bottom row. On the right matrix, right down the vertical column, and each corresponding element. This belongs in a spot, essentially where those rows and columns intersect. So you notice we just did the top left term. If you wanted to get the leftmost term in the second row, well, you would take the second row here, but the left column, the leftmost column in the second matrix. So it'd be 8 times 4 plus 3 times -5, and hey, look, I even got that one right as well. This produces an interesting result now that we produce a 3-row, 4-column matrix as an output, even though that's bigger than either one of the input matrices. And then the final answer after doing all the component mathematics is given right down here at the bottom of figure 214. And that's what you'd really be looking at in MATLAB if you want to do the same thing. Speaking of which, we might as well do that. I've got MATLAB pulled up here on the main screen. Let's just go ahead and assign a matrix A. Oops, A equals. Use a square bracket. So that's one right above the enter key, a little bit up to the left. Let's enter in the first row 2, -1. To go to the second row, we use a semicolon. That indicates the row change. Let's do 8 and 3. Semicolon for the third row, 6 and 7. The space gives that differentiation. Press enter, and we've stored that leftmost matrix in memory. We didn't have to, but that way if we mess up, we can just call it back real quick. Notice, as we gave mention to in the previous video about MATLAB, the variable shows up on the right. Let's get the B matrix established. This will be 4, 9, 1, -3, semicolon, -5, 2, 4, 6. Close it off. There you go. There's the B matrix. And now we should be able to just say A times B, and we're done. Does that match the output? 13, 16, -2, -12. Yep. Second row matches. Third row is correct. Hey, look, the book didn't screw up. Thankfully, I didn't either. But that is a simple example of by hand wrote matrix multiplication. I would definitely encourage you to reference figure 214 if you've never seen that process carried out before. And just as an explanation or a demonstration, let's try switching this up. This should not work, and MATLAB is kind enough to tell us that we've made a mistake and the matrix dimensions must agree. One other thing that's interesting about MATLAB. So we have A times B matrix multiplication. You can, let's see if I can get this right, if you put a period after the multiplication factor, maybe it's before. Yes. So that is a proper error for us to receive. If they were the same size, you would actually be doing not true matrix multiplication, but element by element multiplication. So if you are working with arrays, and you happen to have a two-dimensional array, say you have an array that is the same, so it'd be A, and you want to do an element by element multiplication, that is how you would carry it out. So 2 times 2 is 4, -1 times -1 is +1, 8 times 8 is 64. You see, it's really just the square of each one of the individual terms of matrix A coming out, because it's an individual operation. If we just did A times A, it shouldn't actually work because the matrix dimensions are not correct for true matrix multiplication. But this is an important distinction to make in MATLAB, that if you want to ever, whether it's division or multiplication or taking the square root or whatever operation you want, if you want it done per element instead of considering it as a matrix multiplication, that's how you carry it out. Put a period before the mathematical operator and you're set. So that's just a little bit of an aside there. Let's get back to the actual discussion of mathematical background, right back to the document camera. All right, what's next? Special matrices. Square matrix, okay, that's highly advanced. It really just means, it's the same number of rows and columns. Not a big deal. Diagonal matrix, pretty straightforward. That is, where'd it go? A matrix that only has entries along the main diagonal of the matrix itself. So in this case, if we said that we modify this initial matrix to read like that, where there are zeros off diagonal, guess what? That's now a diagonal matrix. So this whole right side can just go away. That would be diagonalized. There's one specific type of interesting diagonal, where it's all ones. That's the identity matrix, called the identity matrix because if you take any input matrix and multiply it by the identity matrix of the appropriate size, you get the input matrix right back out. It's basically like multiplying by 1 in matrix form. Not a big deal. Upper triangular matrix is where you would have information. I guess it's easy enough to erase. In the upper triangular quadrant, lower triangular is where you do exactly the opposite. The numbers are just made up here. They're not specific. It's just where the data is held. And keep in mind, this could be a 2 by 2. This could be a 7 by 7. It could be of any size. I'm just keeping it simple, keeping it small. So we've gone through those special matrices listed there. A zero matrix, well, surprise, that's a matrix full of zeros. In fact, MATLAB has a nice initiation function if you want to see that. I believe it's zeros. Yeah. So if you want to ever initialize a matrix without any data in it, there you go. And you can also, I think you can just do one number. It makes a 5 by 5. Yeah, there we go. So that's just one of those handy matrix inputs. Does it have a 1? Yeah, it does. So there we go. Ones, zeros. There's a magic matrix function. Several different ways and shortcuts. One of those pre-canned functions for MATLAB to help you initialize your variables when writing code. Okay, going back. Inverse of a matrix. This is one of the biggest and most important operations you can perform on a matrix. So let's see here. The best way to describe why an inverse of a matrix is so important is best written out, perhaps. If you had a matrix which we will just call A. A times X, which X is our set of solution vectors, equals some output B. And what this really means in reality is you have A11, A12, A21, A22, and that's just for a 2 by 2 example. You could certainly go up higher. You could do 3 by 3. You know the drill. You have X1 as an unknown variable, X2. That would be technically an array or a 2 row, 1 column, a 2 by 1 matrix. And the outputs would be essentially your solutions. So what this represents, what this is a common way to write, is two linear equations. This would be the equivalent of saying A11 times X1 plus A12 times X2 equals B1. If you perform the matrix multiplication, that's exactly what you end up with. Second equation here would be A21 times X1 plus A22 times X2 equals B2. So that is the linear system of equations we are seeing simplified or represented in that 2 by 2 matrix system of equations. So I started on this whole discussion when we reached the idea of matrix inversion, because this is one of the most important things an undergraduate student can learn how to do with matrices. The importance comes from the fact that if you multiply the left-hand side and the right-hand side both by A inverse, something important happens. This combination becomes the identity matrix. So you end up with I times X equals B A inverse. So I times X we know is the definition of identity, so that means X equals B A inverse, and that is the description of a solution. X was the vector of our unknowns. So if we can now define our vector of unknowns by taking the solution and multiplying by the inverse of A, we solve the whole problem. You can solve gigantically complex fluid problems that are linearized by making a large matrix of all the different combinations, inverting it, multiplying by your set of answers, your known boundary conditions is what those really represent, and you're done. Well, I mean, the computer's not done. It's going to work really hard for a while, but your job's finished. So that is the core and the crux of finding an inverse of a matrix. There are a few shortcuts to finding that for small matrices, but for the most part we will be doing this numerically and covering ways to find that inverse in a numerical sense. So something that can be handy as a reference, we'll call it. A reference for when order matters, what mathematical properties transfer to matrices, which ones do not, is the list in section 2.4.4. Give that a read. I'm not going to sit here and recite it for you because it's already really about as concise as you could ever hope to make it. Some things are as simple as saying, like, oh yes, the transpose of a transpose is back to original, and of course the inverse of an inverse is back to original. So some things just are pretty common sense. Determinant. You've probably taken determinants. You've probably seen the utility of determinants for matrices in several places. The hand operation of finding determinants is rarely performed above a 3x3 size. When you have computers available, when you have calculators available, 4x4, 5x5, you can do them by hand. There's nothing saying you can't. It's a process. It's laborious. It's possible using the generalized form described in the book. But why? The whole purpose of linearizing these equations to put them into a form that a computer can accept is to have the computer solve the problem for you. So if you get to something that large, use the computer, please. Save yourself the time. But anyway, for a demonstration of finding the matrix, or finding the determinant of a small matrix, let's do the n equals 2 example here. So again, you see the same notation, A11, A12, A21, A22, and the determination is very simple. You basically take upper left times bottom right minus top right times bottom left, and that gives you, in fact, I could highlight it right now, gives you that simple formula, which I would encourage you to highlight in your book as well, for the determinant of a 2x2 matrix. Now that simple formula gets a little bit longer for a 3x3, but there's a pattern that makes sense. If you notice on the 3x3, that is the that is the upper left coefficient, A11, times the determinant of now the middle, basically the bottom right quadrant matrix. Second one is A12, that's the middle term, times the determinant of the 2x2 formed by the 2-1, 3-1, 2-3, and 3-3 terms. So there's a pattern that emerges. And this pattern is what's duplicated for higher order matrices, but really you can see this gets crazy beyond a 3x3, and I really wouldn't suggest doing it at 4x4. So A13 again, you multiply A13 by the determinant of the bottom left, you call it a quad set of matrix. So that is how the pattern emerges and how you would go about determining the determinant of a 3x3 matrix. And immediately putting that to use is Kramer's rule. We just covered matrix inversion as one method of finding a solution to a set of linear equations. But Kramer's rule allows you to essentially surgically extract one answer. Say you're in a problem set where you have 1,000 different linear equations, but in honesty, you only care about the output of one. Sometimes aircraft stability is a reason we would extract one solution without having to solve the entire problem. We're only concerned, is the aircraft stable or is it not? And that can usually be determined by the sign of an exponential term. So in this arrangement, you come up with a whole series of equations, you come up with a whole linear set of elements, but what really matters is you take the determinant of a modified matrix divided by the determinant of the original matrix. Now this modification is the critical part. You substitute in the solution vector for one of the columns of the unmodified matrix determinant. So let's go straight down into example 2.2 for a good description of what's going on. So they are looking for what amounts to the x1 answer. So the bottom determinant of 20 has been found with their source A matrix. So in this step 2, they've calculated the determinant of A, unmodified. That's the source equation. You can see they've just taken a linear set of equations, put it in matrix representation form. Variables are x, y, z. Answers are 5, 3, and 1. Found the determinant of the base matrix. Nothing fancy there, following standard procedure, and it was 20. So place that in the denominator, but the modification happens when you look at what matrix they're taking the determinant of up top. The second column matches. The third column matches the original, but look at the first. They substitute, just direct substitution, nothing fancier than that. Very simple, just take the answer vector, substitute in for the first column, find the determinant of that new matrix you've formed, which they're doing here, in that intermediate step, and the answer for x1 is suddenly 1. Now, this method only shows you one answer at a time. To find x2 using the same method, do they continue on and do that? Hey, they do. How polite. You substitute in the solution vector for the second column. And then to find the x3 solution, you substitute in the solution vector for the third column. So that's how you essentially dissect and extract the solution you're looking for. If you don't need to know all 3 x values, if they're meaningless and you only need to know x2 for whatever portion of the problem you're interested in, this can save you some time. The terrifying part is you can actually do this in some graduate level mathematics courses with a matrix of equations. So now you're not just multiplying scalar coefficients, you're multiplying a matrix filled with subsets of equations together. So in that point you can see where inverting a matrix of algebraic equations would be terrifying. So sometimes just using Kramer's rule to extract one solution that matters is all that you would care to do. So this brings us to discussion of ordinary differential equations. They come in 2 distinct varieties. Linear, which is called standard or canonical. You notice I'll be hitting on most of these bolded terms. Well, they're bolded for a reason. I'm going to stick with that. The linear equations all follow the exact same style and rubric. Don't confound yourself too terribly long with what is a linear equation, what's not linear. A linear equation will have a scalar multiple, a linear multiple of some derivative of the base variable. So you see in the form listed right here, right underneath section 2.5, I suppose that is equation 247. That is the standard canonical linear form of ordinary differential equations. It's called a homogeneous differential equation if the right-hand side equals 0. That's basically what we call the input, the forcing function, or a non-homogeneous equation if the right-hand side is non-zero. Like, say you have a sinusoidal excitation, you have some sort of forcing action being taken on the physical system. That's usually where it would be input. So you can see that there are any number of order of derivatives here. First derivative, second, nth derivative, and then it goes all the way to the end. So that can be expanded as far as you like, and that is the linear ordinary differential equation form. The order of that differential equation would be the highest order derivative taken. Simple as that, pretty straightforward. Nonlinear. This is why we start developing numerical methods. Linear differential equations are simple enough to solve. Basically, everything comes down to some sort of exponential assumption. You solve for exponents, you solve for coefficients, and you're done. It's not, in the end, a massively challenging set of differential equations to solve. Nonlinear ODEs, however, can be challenging, if not impossible. Sometimes it's hard to just find out if this is a stable system or an unstable system, and there are techniques to pursue that, mostly energy methods. Examples of nonlinear terms that would make a otherwise ODE problem nonlinear would be perhaps the presence of trigonometric functions attached to your dependent variable. In this case, you have y times its own second derivative, so that's the variable of interest multiplied by the second derivative of the variable you're tracking, where if that y was on the left just replaced like a 2 or a 3, not a big deal. But that makes it nonlinear. Here you have a derivative multiplied by a second derivative. Again, nonlinear. That's kind of a product. Think about trying to represent these in matrix form. That's what you should think of when you are trying to make the linear or nonlinear assumption. The y variables and their derivatives become your states. Those are essentially your unknowns because you're solving for y as a function of time, y prime is a function of time, y double prime is a function of time, so on, so forth. If you are multiplying those derivatives by its own variable, you will have unknowns inside your matrix and make an unsolvable system. So be sure to go through this. In this case, it's a tangent of the base function, which you could envision that move to the left, and that would become, put it back in the homogeneous type form. So it's pretty straightforward to determine if things are linear or nonlinear ordinary differential equations. If you need a refresher, which you've had a whole course on how to solve differential equations, there is a quick refreshing here, but basically what it comes down to is the assumed solution right here under 253. Y equals e to the unknown power, or unknown coefficient of x. By you assume that solution, use whatever method you care to find the unknown values remaining in the equation, and if it's a linear ordinary differential equation, you're more or less done. Functions of two variables. We're in college now. We do things the more complicated way. Think of a map. Maps are functions of x and y, right? If you imagine some sort of weather, a volumetric density plot, that'd be a function of 3 dimensions. You would have to have a latitude, longitude, and an altitude to determine what the density is of that air particle at that point. So that's really all we're saying here, is that a function of x and y, well, has 2 inputs and perhaps, hopefully, always, 1 output. So that functional value changes with 2 input dimensions. Simple as that, not a big deal until we start doing some more complex multidimensional functions later on. Partial derivatives of higher order. Oh, skip to the original partial derivatives. There we go. So this is again just getting into the base calculus definition of derivative. You remember that from our discussion of the earlier parts of chapter 2. But now with the partial derivative, you acknowledge the fact that your function is a function of both x and y. So now you have to distinguish that you're taking the derivative of your function f with respect to x. Notice that you're not incrementing the y variable in either one of these functional calls. You're only changing the x direction. Similarly here they find the derivative with respect to y, and in that case x stays the same as you are discovering the change in the functional value across some delta. It is the y variable only that's changing. The simplest way I can possibly describe the partial derivative of 2 dimensions, if you don't already have a good hold of this, is you're on a hill and you can have a different slope going north and south than you would having going east and west. If you've ever gone hiking for a long period of time, I'm not a hiker myself, but I have friends who've talked about it probably more than they should. But they choose the route up challenging mountains to minimize the gradient, and that has them look at both the, you could separate this down simplistically to the north-south derivative and the east-west derivative. They combine them to find essentially the lowest slope. Seldom do I meet a hiker that wants to take the steepest path up the mountain. They will sacrifice distance to be able to take a lower gradient. Partial derivatives of a higher order, well, you basically just keep going. You employ the same formula, but then you take the derivative of the function you've already taken a derivative of. Especially in numerics, this is very easy to execute. You take the same idea, apply it to the derivative until you can no longer take an additional derivative. Not every function is infinitely differentiable. If you have a constant value, the derivative of the constant is 0. It has no slope. It'd be constant everywhere. The derivative of 0 is 0 again. I mean, you can take the derivative, but you're going to get the same answer, and it's going to be nothing. So not everything is going to have an infinite set of derivatives, though some functions do, namely periodic functions like sine and cosine come to mind. They're infinitely differentiable. So, chain rule is pretty important in engineering, and a lot of students, a lot of instructors even, oversimplify some important derivatives. So you can see here they've taken the chain rule differentiation of a function of both x and y. And pay attention to 263 because we're going to draw a comparison of this to a very, very common engineering equation here in a few seconds. But notice they take the derivative with respect to x multiplied by dx plus the derivative with respect to y multiplied by dy. And that gives you the total differential of the functional value of the function f. So let's think about a different engineering function. Let's go to the surface. Force. Force, by definition, is the time rate of change of momentum, where momentum we can represent as dp, dt, that's time rate of change of momentum. So momentum is commonly variable p. And we know momentum is mass times velocity. So this is obvious, you know which engineering equation this is headed towards. It's headed towards F equals ma, but that's not the entire picture. You've been a little bit lied to for most of your engineering life so far. So if you take this more explicitly, f equals the derivative of mv dt. But now think about it, you actually have to use the chain rule to differentiate those two variables. This becomes mass times dv dt plus velocity times dm dt. So it's only in the circumstance where dm dt is 0, meaning that mass is constant, that this simplifies down to the equation F equals ma. In a system that could be expelling mass or changing mass during its flight, rockets, this is obviously not true. So it's only through bookkeeping this v dm dt term as essentially the thrust of the rocket, in addition to the base F equals ma term, that we have accounted for this without having to teach every single student the true chain rule expansion of F equals ma. The most explicitly true definition is given there in the red box. That is the deeper F equals ma term that you can remember that more accurately describes the circumstance. So if you have a system that is losing mass or perhaps it's gaining mass over time, that is the better way to represent it. But okay, that was a bit of an aside. I give up. Not really. Document camera, here we go. Back to the next topic, Jacobian. This is one of those mathematical terms. It's actually very simple to understand, but it makes you sound really smart when you can talk to somebody else about the Jacobian, because they don't really teach those in high school. So like, he must have some of that high-level collegiate math. Or she. I'm not just talking to guys here. All right, fair enough. Jacobian. Derivatives. So if it is a two-dimensional function, x and y, you'd end up with a 2 by 2 Jacobian. So you take the first function, perhaps a system of two functions with two variables in each. This would be the partial derivative of function 1 with respect to x, partial derivative of function 1 with respect to y. Second row becomes the partial of function 2 with respect to x and y. And you imagine how this can grow for functions of x, y, and z, or systems of equations of that order. Typically, if you have three unknowns, you'll have three equations, so it works out. It's just a matrix of the partial derivatives of those functions. The Jacobian determinant is just finding the determinant of what really amounts to finding numeric derivatives, most commonly, of this Jacobian matrix. This comes up in a lot of dynamics problems when you're viewing dynamic systems in very generalized terms. So think flight controls class, if you're going to be taking that in the future. And lastly, something we've already discussed in class a little, but it's nice to see the explicit formula of Taylor series expansions. You've certainly seen this in calculus class. I know every undergraduate student loves these Taylor series so much, and we get to revisit them here. So by definition, you can represent a function with increasing accuracy as you step away from that function by expanding out the series here. So you're at some location x naught. That's your initialization location. Notice that x naught is the same for each one of these terms you're adding. So you have the initial functional value at x naught plus some deviation. You're going to travel some distance, x minus x naught. That'll be a distance. Maybe it's a 0.1, maybe it's a foot, whatever. Who knows what length scale you're solving a problem in. But it'll be a distance times the derivative of the function taken at x naught. And then to add a second term, the second derivative would be the distance squared divided by 2 factorial times the second derivative taken at x naught, the point you started from. You do that for the third term and the nth term ad nauseum to infinity, as long as that function is infinitely differentiable. If you run out of derivatives, I think you're finished. But for a function like sine or cosine that is periodic, that will just keep going and going and going. This does have a nice graphical representation of how the accuracy of the system is improved by adding more terms. This is on page 49. It's example problem 2-3. And you can see that as you deviate away from the 0 point where they're treating it as x naught, even with just a single term, the deviation is not significant out at 0.5. It's only whenever you want to start having deviations of a unit or 2 units of length that you start to see significant departures from the true values shown in red to the values approximated by 2 terms, 4 terms, 6 terms. They've shown several. Even with 6 terms, once you travel more than 2 units away from the initialization point, it's not terribly accurate. You need to keep taking quite a few higher order derivatives and including many higher order terms to make this Taylor series expansion accurate at long distances. The point is that it's really, really good when you're close to the location you're taking the partial derivative, or taking the derivatives at. So if you only wanted to estimate the function out to 0.01, 1/100th of a unit away, which is pretty common for numerical techniques when we're just estimating derivatives or when we are looking at the slope of a particular area, that's pretty simple. That's why Taylor series expansion is a very useful way to linearize functions for use in numeric problems. You can also do this for 2 dimensions. You start taking partials. So again, you have any number of ordered terms, though the description is getting a bit longer. The difficulty is not. You have this base functional value at x naught, y naught. Now you have 2 points of departure. The not terms, of course, indicate that. You still have the factorials that show up, 1 factorial, 2 factorial, 3 factorial, and then n factorial. X minus x naught is your deviation, again, just in the x direction. Notice now you're just taking the partial, del f, del x, taken at x naught, y naught. So again, all of these partials are taken at the originating point. That point doesn't mean the origin, it just means where you are sourcing those derivatives from. That's probably your last functional evaluation from a numerical perspective. Y minus y naught is, of course, the deviation in the second direction. You're taking the partial in the y direction. It makes sense. Really, you're just doing the same operations in 2 orthogonal directions. You might imagine x as the east-west vector direction and y as the north-south vector direction. And this allows you to put a 2-dimensional approximation of that function that is really accurate in the near distance, but not so great in the far. So to finish up the chapter, we end with inner product and orthogonality. Wow, can't pronunciate. Orthogonality is being perpendicular. If 2 vectors are orthogonal, and you take their dot product, meaning multiplying them together, you get 0. Dot product can also be viewed in vector sense of projecting one vector onto another. If you remember, that is because they have that cosine handy-dandy relationship where the magnitude of 2 multiplied by the cosine of the angle between them becomes the dot product. Well, if the angle is 90 degrees, what would that be? That'd be pi over 2. Hopefully I did a quick trig right in my head. That cosine term comes out to 0. Makes it go away. So that means they are orthogonal functions. This can also be used to prove if 2 vectors are parallel. If they are parallel, whether they're in opposition or in the same direction with one another, you will get a value of 1. If they're exactly in alignment, you'll project one vector onto the other and get the entirety of those coming back to one another.